Welcome to Chemical Reactions, continuing the presentation series. This is Chapter 8 of our current textbook, of course. This corresponds with Section 3, although it will go beyond what is in Section 3 at some point. Section 3 does talk about predicting. It talks specifically more so about single replacement than others. However, we will talk about how to predict both double replacement reactions, which are really simple, I believe. Also, single replacement reactions, which are equally as simple, but there's a little bit of a there's a list you have to look up on, or you have to look at a list in order to make the prediction. And of the synthesis and decomposition, we will also talk about those, but that'll be in the last presentation, and that'll be part 5. Of course, student learning map here. You can pause if you need to look at it. Likewise, you can pause here if you need to look at the lesson question. We're not doing a student learning map, of course, but the questions themselves are very relevant, very important, and would show up on a test, of course. Okay, categories of chemical reactions and predicting products. So Chapter 8, Section 3, and this is Part 4 of the presentation series. Okay, so here's a disclaimer. I certainly am very well aware that all double replacement or double displacement reactions do not occur. However, it is beyond the scope of what we're going to talk about as far as, when do they occur, when do not occur, when should I predict, when should I not predict. We're going to predict them all as if they happen. So don't worry about that. You come back to Chemistry 2, we will talk specifically about when they don't happen at a future date. So it's no big deal. Now, we will say, though, that not all single displacement or single replacement reactions will occur, and we will predict when they do and do not occur by using a list called an activity series, which simply has a list of selected elements lined up top to bottom, typically is how it's presented. And at the top of the list, they're very reactive. At the bottom of the list, they are relatively unreactive, and that's how we will be able to judge when single replacement does or does not happen. All right, so let's talk first about a double replacement reaction. So in a double replacement reaction, if my pen is activated here, basically, as we talked about in the previous video very quickly, the cations are simply exchanging their anions. So that's all they're doing. They're just doing a quick swap. And that's the double replacement reaction. It is literally that simple. There's a little bit of a catch, and I'll tell you about that in a moment, but that's something, a skill you already have anyway. So consider this. We have this compound AB, and we have compound DE. Well, how do I know what the cation is? Remember, the cation is always the first thing written down if it's ionic. And we're not going to do this for covalent, so they're all ionic. So therefore, what I'm going to see is A and cation D will exchange places. They do not bond together, because you would be asking two positive things to bond together, and remember, they would repel each other. So they're going to exchange places, and when they exchange places, you end up with compound AE now. Remember, the positive comes first and the negative comes second. And then compound DB. Remember, D is positive, so it has to be written first. Now, we don't do a lot with this generic stuff. This is just good to show exactly what's going on without getting confused with these specifics of compounds. But that's all you got to do. You're just exchanging them. All right, now let's do one for real with calcium chloride down here and aluminum sulfate. So with calcium chloride, CaCl2, calcium, of course, is my cation. Aluminum is the cation. They are going to effectively exchange places. When they do this, the calcium, I'll just write that one down first because it's the first thing I see. So calcium is going to combine with the sulfate. But before I write calcium sulfate down as a formula, I actually have to create the formula, and that means, and here's the catch, that means that you got to create the formula from scratch. So you got to go through the oxidation numbers. You got to see if they crisscross or reduce before you actually write the formula down. You can't just grab calcium and the sulfate and jam them together on the other side of the arrow like I did the A's and E's and D's and B's and call it good, because you may have incorrect formulas. Well, what I see with calcium sulfate is a 2 positive and a 2 negative cancel, and so CaSO4 is certainly that formula. And then I'm going to have an aluminum and a chlorine formula. So that aluminum has Al with a 3 positive charge. Chlorine or chloride is a -1 charge. They don't cancel, so I must crisscross, and so the formula here is AlCl3. Notice, had you just taken the aluminum and the chlorine, you might have ended up with like Al2Cl2 if you're just jamming them together. That certainly is not the formula. And if you saw that, you might have went, oh, maybe I need to reduce. And so AlCl. And again, that's not the formula either. When you're creating new formulas, you gotta start from scratch and put the oxidation numbers down and see if you crisscross. Otherwise, it's just exchanging. So the calcium and the sulfate combine together. The aluminum and the chloride combine together. It's just like the generic up there. All double replacement reactions do exactly the same thing. So that's very consistent, and so I feel they're very easy to predict. The hitch in the system is you got to create the formulas when you come over to the other side of the arrow. Now, of course, I do have to balance this thing. So let me get rid of just a little bit here and balance this. Okay. So to balance, I have 1 calcium on the left, 1 on the right, 2 chlorines on the left, 3 on the right. Ooh, 2 and 3. This is an odd even situation. So let's make it a low common multiple. 3 times 2 is 6 chlorines. 2 times 3 is 6 chlorines. So 2 aluminums now, because I'm right here, 2 aluminums, 2 aluminums, 3 sulfates here, and I would need 3 sulfates here because I can balance it as a unit, and then 3 calciums actually then balance with my other 3 calciums. So there's my tally, and it seems to work out. Let's move on to single replacement reactions. Okay, in a single, and sorry if the font down here, the colors don't show up very well. Because I'm in the presentation, I can't change those colors. Single replacement. We have a lone element is attempting to replace a similar element, like a metal replacing a metal, or a nonmetal replacing a nonmetal. That's a like element. So a lone element will replace its like element in a compound. So metals attempt to replace metals. Nonmetals attempt to replace nonmetals. So if I have element A down here and it is a metal, element A is going to attempt to replace element D, because D would be the cation and D would be the metal. Well, if it occurs, then A will kick D out of the compound, will take E for itself as its anion, and then D just gets kind of stuck to the curb. It just kind of gets kicked out of everything, and D becomes then what we call a free element. So free element, that's horrible writing, but anyway, free element. Okay, down here, in this case, element B is a nonmetal, and you would be able to recognize that because of your knowledge of the elements in the periodic table. When B is reacting, B is attempting to kick E out of the compound. Now, they don't bond together, they're going to kick it, it's going to kick it out. If it will, then you're going to end up with D, B, and then E is jammed out here as a free element because there's nothing for it to actually react with at that point. Not all of these reactions occur. Basically, A has to be much more reactive than D. B has to be much more reactive than E. If it happens, we'll be able to predict the products. If A is weaker, chemically speaking, if B is weaker, chemically speaking, then it is no reaction. And if it's no reaction, then you can't predict a product because nothing happens at that point. So how do we determine when A or B is more reactive than the thing it's trying to replace? Metals replacing metals, nonmetals replacing nonmetals. Well, let's check that out. So to react or not react, that is the question, right? To kind of paraphrase a Shakespeare quote. Well, first bullet. If the element in the compound is more reactive than the lone element, the reaction will not occur. So if the element in the compound is more reactive than the lone, then the lone can't kick the compound element out. It just can't. And so the reaction will not occur. The lone element is not chemically strong enough to break the bond, because that's what that lone element has to do. It has to be strong enough to break the chemical bond in order to make its own new compound. So how do we predict when single replacement or single displacement reactions will occur? We are going to use what is called an activity series. And that's simply a list of elements that have been decided upon through experimentation. We just take these elements and experiment and experiment and experiment, and we are able to list, hey, this one's very reactive, this one's not as reactive, and this one's not reactive. And we do that for most of the elements. So let's see what that list looks like. Okay, I thought the activity series list was coming up, but that must be next. So how do we use the activity series? Well, basically you would have a list of elements from lithium, sodium would be on there lower, and then cadmium would be on there even lower, and then platinum is clear down at the bottom of the list, I think. And there's a bunch of things in between. So essentially, the lone element, so if you're talking, lithium plus sodium chloride, will this reaction occur? The lone element is lithium. It has to be higher on the activity series than the element it's trying to replace. Well, lithium is a metal, it's a cation. Sodium is a metal, it's a cation. So lithium is attempting to replace sodium. Lithium has to be higher on our activity series. If lithium is higher than sodium, it will occur. If lithium were lower, it would not. Well, lithium is higher, and so this reaction will occur, and then you would say, okay, +1, chlorine is a -1, they balance, so LiCl, and then sodium is kicked out of the compound and it becomes a free element. So we predict that, and it works. If lithium were lower, if I tried to do the same thing with cadmium, so cadmium plus sodium chloride producing. Cadmium is a metal, sodium is a metal. Cadmium as a free element must be higher for this reaction, and cadmium is lower. So sad face. Actually, that's a mad face. There's a sad face. So this reaction will not occur. Cadmium is not strong enough to break that chemical bond up. So hopefully now let's see the activity series. Finally. Okay, so here is a portion of the activity series, and this is a handout that's available in the Google Classroom in a handout section for Chapter 8. And this activity series is exclusively used for us for single replacement reactions. We will not need this list for anything else, and you do not have to memorize it. I never have anybody do. You just have to know how to use it. Effectively, this list is where it starts most reactive. So up here at the top, all of these elements are very, very reactive. And the farther down you go on this list, the less reactive everything becomes. And there's some qualifiers as far as there is some explanations about what they will react with and in what conditions. I'm not so concerned about that other than just understanding the list. Remember that the free element must be higher on this list if the reaction occurs than the element that's in the compound. Okay, let's move on. This is, by the way, activity series of metals. So almost all these are metals, except you will find that hydrogen, while it's a nonmetal, is not on this list, or is on this list. It's not a metal, but that's because metals react with acids, and hydrogen, of course, is the effective component of an acid. And so hydrogen actually appears on the activity series of metals because it acts as an ion and it reacts with metals in an acid form. And so that's the cutoff. If anything is above hydrogen, it will react with an acid. If it's below hydrogen, then that substance is inert in an acid. Okay, otherwise it's all metals. Also, however, a activity series of nonmetals. And of course, nonmetals, there's a lot less nonmetals on the periodic table. And this is not even a complete list of that. This is really only just 6. 1, 2, 3, 4, 5, 6. Yeah. So this is a very short list, and this list is independent of the metals. So when you compare elements, you're only looking at one or the other list. For convenience, I simply put this on the same sheet, and this is at the bottom of the sheet, and I have separated it with a gray bar, so it looks like it's a separate list. All right, and how do you read this? Well, fluorine. Fluorine is the highest of the reactivity. Sulfur is the lowest. So fluorine can replace anything. Sulfur can't replace anything above it because it's the bottom of the list. Okay, let's do some examples quickly. So here I have chromium phosphate reacting with barium. This is a single replacement reaction. I can see that because I have an element and I have a compound, so I know automatically it's a single replacement, and with a single replacement I automatically consult the activity series. That's just kind of how that strategy should work. So let's look for barium and look for chromium, because barium is a metal, chromium is a metal. Hey Spence, how do I know that? Well, you got to know your periodic table, something that we've been working on for a long time. You got to be able to know, looking at barium, it's a metal, or look it up on the table and know it's on the left-hand side of the metalloids, and yeah, it's a metal. Chromium is in the same spot as far as it's on the left-hand side of the metalloid, so it's a metal. So metals replacing metals, barium has to be higher than chromium. So let's come over here and find barium. Okay, so barium is actually very close to the top. So as a free element, barium is pretty high. It looks like it should, whereas chromium. Well, chromium is way down here. And so yes, this reaction will occur. Barium, the free element, is higher. So it is higher. So it will occur, and I can predict. So barium, 2 positive charge. Phosphate, PO4, has a 3 negative charge. I got a crisscross. So that, and I do have to keep parentheses to make that. Then chromium is simply booted out of the compound, and there's chromium as a free element. Balancing, I would have to balance 2 phosphates, 3 chromiums, 3 chromiums, 3 bariums, 3 bariums. So there we go. Okay, let's move on and do a couple more of these. Let me clean this up just a little bit here. And I certainly don't need these now. All right, so let's do gold and hydrogen chloride. Now, gold is a metal, it's a cation, and hydrogen is the cation here, even though it's technically not a metal. But remember, this is an acid, hydrochloric acid, so how is this going to work? Well, let's find gold and hydrogen. So on the period, or on this activity series, swapping the colors out, what I do is I find right there, there is hydrogen. And gold is actually below it, way down here at the bottom. I thought platinum was at the bottom, but actually it's not. So there is gold. Gold is way below it. And so gold is very unreactive. It's not chemically strong enough to separate hydrogen away. So this, no reaction. And that's all you got to do, no reaction. There's no balancing, no anything. Just indicate no reaction. I wouldn't leave it blank, though, because it looks like you didn't do the problem at all. So I would write NR or just write the words no reaction or something like that. I oftentimes use RXN for reaction. So here now we have fluorine and sodium chloride. Okay, well, fluorine here you got to recognize is a nonmetal. So nonmetals replace nonmetals. I got to compare it to the chlorine now, so I can't look at the sodium. And in fact, if you're using the activity series, fluorine and sodium are not on the same list, so you can't compare them. Well, I come over to the bottom list that I've got this just little inset down here. So here's fluorine at the very top. Chlorine, even though it's very close to the top, is below it. So fluorine can make this happen because fluorine is higher. Fluorine is the free element. So this reaction will occur. Sodium is the positive ion, remember, positive 1, so it has to be written first. And then fluorine, which is a negative 1, is last. They balance, and so just NaF. And then chlorine is a free element. Notice chlorine is one of our 7 diatomic elements, and so when I wrote Cl down, I can't just like up here with the chromium. It's just, you know, chromium's not diatomic. You can just write Cr, and it's okay as an atom. Chlorine is always a molecule. It's not an atom. It's going to form as a molecule. And so the 7 would be, remember, hydrogen, nitrogen, oxygen, and then fluorine, chlorine, bromine, and iodine. Here is where you have to know for these 7, you got to be able to write them as a free element with the molecule, with the 2. Okay, let's move down here to the last example. Here I have chlorine, and it's a nonmetal. And we're trying to replace a nonmetal, which is fluorine. Okay, so it's actually kind of almost the same question, except that, if I erase in here, that chlorine is my free element, and it is lower. Because it's lower than fluorine, no reaction. And that's how single replacement or single displacement reactions work in concert with the activity series to tell you when to predict them. And when you predict them, you got to balance them. And by the way, the third example down I didn't balance, so I would have to have a 2 in front of the sodium fluoride and a 2 in front of the sodium chloride to balance. So that one balances now. Okay, let's move on. All right, so variable cations. What do we do here? Okay, remember variable cations, it's your table B, and I want to draw your attention to this. Let me go ahead and change the color here, something that stands out a little bit. Maybe this color. Okay, notice in copper, copper 1 up here. So I have copper 1 with 1 positive charge called cuprous, and then I have copper 2 right here with, copper number 2, cupric, Cu2+. Notice this is in bold print. That is important at this moment. Notice in cobalt, cobalt 2 is in bold print. Notice in gold, gold 3 is in bold print. Iron 3 is in bold print. Lead 2, mercury 2, nickel 2, tin 4, tin 4, good buddy, a little bit of CB humor there. Chromium 3, manganese 2, all the way down here, tungsten 6, thallium 1, and then titanium 4. Notice all those are in bold print. The bold print is right here. The bold print is the most common form of that ion. So you never have to actually guess, hey, what's the charge of this copper in a purely just chemical setting where there's no other indication of what copper's charge should be? Well, if you had to guess it, copper 2 would be a good guess because that's the charge it's going to most commonly form. And with all of these and with the periodic table, if you look at the other ones that are not on this list, same idea. So let's see how that's going to work. Okay, so why would it be important to understand common charge and if you had to guess, right? So because we're not in the business of guessing, you know, we like to know. Okay, well, let's check these examples out. Now, I went ahead and confirmed with all of these that all of these examples will work because I did consult with the activity series, and all of the free elements are higher than their counterparts in the compound. So these will all happen. That way I didn't have to reproduce the activity series on this slide. But what I did want to do was I wanted to reproduce the variable cations, so we could take a look at that. So this first reaction with chromium nitrate and manganese, so that'd be technically chromium 6 nitrate, this will occur. So when it does, I would write my equation, so here, or my formula, here is Mn, and I would have it combining with nitrate. I'll put that in parentheses. Well, nitrate has a -1 charge every time. That's something you can have memorized. But what about manganese? Manganese has a bunch of charges. So which charge would I want to then use? Because there is no indication in this example as to what charge to use. Well, without any additional information, I'm going to consult either the periodic table or my ion sheet. They both say the same thing. Down here, I think I have to change the color right there. That one tells me that manganese 2 is the most common form of the charge, and that's the one I'm going to go with without any additional information. Well, 2 and 1 don't cancel, so I have to crisscross, so it's MnNO3 2 in parentheses, and then I'm going to write chromium out here. Chromium can be just written this way. It's not one of the 7 diatomics, and so I don't have to worry about chromium other than just writing Cr down. It's okay as a single atom. I should balance, though. With the nitrates, I have 6 nitrates, and I only have 2 nitrates, so 3 times 2 is 6. 3 manganese, 3 manganese, and then chromium's 1 chromium and 1 chromium, so that one actually balances. Okay, let's do the iron and the hydrochloric acid. Again, I've confirmed this reaction will occur, so therefore I will have an iron combining with a chlorine. Chlorine always has a -1 charge, but what about the iron? Well, here again, the iron, we want to go up to iron, and we notice that iron 3 is the actual common charge there. And so I would, if I had to guess, I would then guess a 3 positive charge. They will not balance, so I crisscross. So FeCl3, and then, whoops, hang on, I was about ready to write something else. What I want to write down, however, is hydrogen, and hydrogen is diatomic. That's a horrible tube, so let me try that again. It is diatomic, remember that, and I'll just come up here into the corner up here. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all form diatomics. And so these 7, it kind of makes a 7 there. These 7, you got to remember when they're free elements, you got to write them as a pair of 2, and then we would balance. 3 chlorines here, 2 hydrogens there. What do I do over here? Well, that's actually a common moldable thing now, if you work it out, because it won't work otherwise. So 6 hydrogens, 3 times 2 is 6 hydrogens, 2 times 3 is 6 chlorines, that works out, and then 2 irons, that one balances. Okay, here we have mercury, in the third example, mercury and gold 1 fluoride. This reaction will occur. I double checked it with the activity series, and so I'm going to create a mercury and a fluorine compound. Well, the fluorine always has a -1 charge, but what about the mercury? Well, if I look over here in mercury 2 without changing the color, mercury 2 is the actual most common ion there. So I'm going to guess mercury 2. 2 and 1 don't cancel, so I crisscross to make it HgF2 plus gold, and gold is not one of the 7 diatomics, so you can just write it that way. To balance, it looks like I need a 2 in front of the gold fluoride to make the fluorines balance, and then I would have to have a 2 in front of the gold to make that balance as well. Lastly, with chromium and iron 2 fluoride, so this reaction again will occur according to the activity series. Chromium is just 1 step higher than iron, and so I'm going to have a chromium fluorine compound. Fluorine is always a -1 charge. Chromium has a most common charge of 3 positive. So that's the charge I'm going to guess. They don't balance, so I crisscross to make a formula of CrF3. And then iron is kicked out of a compound and becomes a free element. It is not diatomic, so I just write it as Fe. Then you go and balance. It's an odd even issue, so I'm going to go with a common multiple because of my fluorines, 2 and 3. So 3 times 2 is 6, 2 times 3 is 6, 2 chromiums, 3 irons, 3 irons. Okay, there you have it. Now, just before, because this is actually the last slide, so I can wrap this up. But just before I wrap it up, I would say, as far as these ions and elements in general, element ions, and that includes also the polyatomic ions, when you have them memorized, that these things actually become so much faster. You can focus on the predicting, you can focus on the charges, you can focus on the formulas that you're writing, as opposed to consistently and continually having to look things up again and again and again and again. You might think it's not worth the time, but wow, I mean, talk about a time saver, and it really allows you to focus on the actual topic, the lesson that you're trying to do, and you're not getting bogged down with, oh, is this a variable cation? Is this a metal? These types of things, which should be basic information at this point. I'm hoping it's starting to really come to you. Okay, well, that's it. This is how you predict single and double replacements. There is a practice sheet that you can do with an answer key to predict, I think, 10 or 11 double replacements and 10 or 11 single replacements. That will allow you to then double check your work because the answer keys are right there as well. The very last presentation for the entire Chemistry 1, actually, because I'm going to end it with Chapter 8. I won't say that. Maybe I'll have a chance to do a little bit in Chapter 9 for the juniors, but otherwise, the very last presentation for Chapter 8, at least, will be on synthesis and decomposition reactions, and there's a little bit more to it with those, so I wanted to make sure that was its own separate presentation. Fortunately, though, they're kind of almost opposites of each other, so you learn one, you learn both, but they are different from this. Thank you. See you in the next presentation.